Picture this. You're here, existing, on a planet, in a solar system, within a galaxy of billions of stars, itself one among trillions, in a cosmos so vast it defies comprehension. You gaze up at the night sky and you feel a profound sense of scale, of history, of purpose perhaps. But what if all of it, every star, every galaxy, every law of physics, every thought, every emotion, arose from nothing? Not from a divine spark, not from some primordial singularity, but from a random, ephemeral blip in an otherwise featureless void. Today, we confront a mind-bending possibility that challenges our deepest assumptions about existence itself. We're asking, what if our universe is just a quantum fluctuation? If you're ready to unravel the fabric of reality and confront the ultimate contingency of your own being, make sure to subscribe to this channel and give a thumbs up. Let's dive into the profound implications of a universe born from pure chance. Let's begin with the very concept of nothing. In classical physics, nothing means an absolute vacuum, an empty stage devoid of matter, energy, or even space and time. It's the ultimate blank slate. But quantum mechanics, the strange and counterintuitive rulebook for the very small, utterly demolishes this simplistic notion of emptiness. You see, at the quantum level, true nothingness doesn't exist. Even in the deepest, darkest void of space, far from any star or particle, there is a seething, churning maelstrom of activity. It's a cosmic froth, an invisible ocean teeming with what we call quantum fluctuations. Imagine, if you will, the seemingly placid surface of a perfectly still pond. Now zoom in deeper and deeper until you're looking at the molecular level. You'd see water molecules constantly jiggling, vibrating, briefly popping in and out of existence in tiny, fleeting dances. This isn't just an analogy, it's a profound truth about reality. According to the Heisenberg uncertainty principle, you can never precisely know both a particle's position and its momentum simultaneously. But this principle extends far beyond position and momentum. It also applies to energy and time. This means that for extremely brief moments, the universe can borrow energy from the vacuum, creating pairs of particles and antiparticles, known as virtual particles, that instantly annihilate each other, paying back the energy debt before any violation of conservation laws can be observed. These virtual particles are not merely theoretical constructs. Their effects have been measured in experiments like the Casimir effect, where two uncharged parallel conducting plates placed very close together in a vacuum experience a small attractive force. This force arises because fewer virtual particles can pop into existence between the plates than outside them, creating an imbalance of pressure. So when we talk about a quantum fluctuation, we're not talking about some abstract philosophical concept of nothing. We're talking about a very real, incredibly energetic and fundamentally unpredictable property of the quantum vacuum. It's not empty. It's pregnant with potential, a dynamic arena where energy, mass, and even space-time itself are constantly in flux, briefly appearing and disappearing in defiance of classical intuition. The vacuum isn't passive. It's a boiling brew of possibilities, a cosmic cauldron where the rules of creation and annihilation play out on scales so infinitesimally small and for durations so fleetingly brief that they escape our direct perception, yet leave an indelible mark on the universe's most fundamental properties. You might think of it as a constant, underlying hum of existence, a background noise in the orchestra of reality that, while usually unnoticed, holds the very symphony within its potential. This isn't some fringe idea. It's a cornerstone of quantum field theory, one of the most successful scientific theories ever devised, explaining everything from how light interacts with matter to the existence of fundamental particles. It describes the universe not as composed of distinct particles, but as vast, interconnected fields permeating all of space. And even when these fields are in their lowest possible energy state, what we call the vacuum state, they are not truly static. They are subject to these ceaseless quantum jitters, these spontaneous fluctuations that momentarily perturb the field, giving rise to virtual particles. These fleeting appearances and disappearances of virtual particles happen billions of times per second in every cubic millimeter of empty space. It's a subatomic disco, a ceaseless, unobservable dance of creation and destruction, a cosmic pulse that never stops beating. And it's from this perpetually restless, inherently uncertain quantum vacuum that some theories suggest our entire observable universe might have burst forth. The implications are staggering. If the universe emerged from such a fluctuation, it means that at its deepest core, our existence is a statistical anomaly, a roll of the cosmic dice. It didn't need a pre-existing space because space itself could be part of the fluctuation. It didn't need pre-existing time because time could have been born in that very instant. It didn't need pre-existing matter because matter and antimatter would spontaneously arise from the borrowed energy. The entire stage, the actors, and even the script would have sprung into being from this dynamic, uncertain quantum foam. And that foam, that ultimate nothingness from which we might have arisen, is still all around us in every atom's empty space, in the vast voids between galaxies, constantly bubbling with the potential for new realities, new universes, new possibilities, all hidden just beneath the surface of what we perceive as solid, stable existence. You are literally swimming in the primordial soup of potential creation, a constant reminder that the universe is far stranger and more contingent than you could ever imagine. The leap from a tiny, fleeting quantum fluctuation to an entire universe, billions of light years across and packed with galaxies, seems impossible. How could something so grand, so enduring, erupt from such a minuscule, ephemeral blip? This is where the concept moves beyond mere virtual particles and into the realm of cosmogenesis, the birth of the cosmos. Imagine a single quantum fluctuation, but this one is not just a pair of particles. It's a fluctuation in the very fabric of space-time itself, a tiny bubble of nascent reality spontaneously emerging from the primordial quantum vacuum. For this bubble to become our universe, it needs an engine, a mechanism to take that initial infinitesimal spark and inflate it to cosmic proportions before it can vanish back into the void. That engine, according to leading cosmological models, is called inflation. Cosmic inflation theory, first proposed by Alan Guth in the early 1980s, suggests that in the first minuscule fraction of a second after the Big Bang, an utterly incomprehensible 1036 to 1032 seconds, the universe underwent an exponential expansion. During this brief, violent burst, a region of space smaller than a proton stretched to macroscopic, even cosmic, scales. This wasn't matter moving through space. It was space itself expanding faster than light, carrying any matter or energy within it along for the ride. And here's the crucial connection to our quantum fluctuation idea. Inflation provides a mechanism for a tiny, quantum-sized seed to grow into the vast, uniform universe we observe today. Think of it like this. A quantum fluctuation is a momentary, statistical deviation from the vacuum state. Most of these fluctuations are incredibly small, appearing and disappearing almost instantly. But occasionally, just by pure chance, a fluctuation could be large enough or persist long enough to trigger a phase transition in the vacuum energy. This phase transition is what would drive inflation. Imagine the vacuum as a giant, perfectly flat plane, but with tiny, random hills and valleys, the quantum fluctuations. Sometimes a tiny bubble forms in one of these valleys. If the conditions are just right, if this bubble contains a specific kind of energy field, called the inflaton field, it could tunnel out of the vacuum state. Instead of collapsing back, it would begin to expand rapidly, driven by the enormous negative pressure of the inflaton field itself. This expansion would be so rapid, so powerful, that it would smooth out any initial irregularities and generate the conditions necessary for the universe we know. The energy driving this inflation would eventually convert into the matter and radiation that populate our universe. The process would be akin to a snowball rolling down a hill, rapidly gathering mass and momentum. That tiny initial quantum fluctuation, given the right set of improbable circumstances, could suddenly explode into existence, stretching space-time to such an extent that it effectively hides its quantum origins, while simultaneously imprinting its quantum characteristics onto the grand structure of the cosmos. The universe in this scenario isn't born from a singular point of infinite density, but rather as a tiny, highly energetic patch of fluctuating quantum vacuum that undergoes an extreme inflationary burst. The beauty of this idea is that it solves several long-standing problems in cosmology. For instance, the flatness problem. Why is our universe so incredibly flat, so close to the critical density required to avoid immediate collapse or infinite expansion? Inflation explains this by stretching any initial curvature to an almost perfectly flat state, much like inflating a tiny, wrinkled balloon to an enormous size makes its surface appear smooth. It also solves the horizon problem. Why is the cosmic microwave background radiation, the echo of the Big Bang, so incredibly uniform in temperature across regions of the sky that should never have been in causal contact? Inflation dictates that these regions were once close enough to interact and thermalize before being flung apart faster than light by the accelerating expansion. So the remarkable uniformity and flatness of our universe, far from being evidence of a grand design, could be precisely the fingerprints of its violent quantum-driven birth. This addresses one of the most perplexing mysteries in cosmology, the punt fine-tuning problem. Why are the fundamental constants of our universe so precisely calibrated to allow for the existence of life? Change the strength of gravity by a tiny fraction, and stars either wouldn't form or would collapse too quickly. Alter the strong nuclear force, and carbon, the backbone of organic chemistry, might not exist. These precise values seem almost too perfect, leading some to invoke a designer or a grand purpose. But in a multiverse of quantum fluctuations, this fine-tuning ceases to be a mystery. It becomes a matter of pure anthropic selection. You exist in this universe with these laws simply because it's one of the rare universes capable of supporting your existence. If the laws were different, you wouldn't be here to observe them. It's like finding yourself in a room full of lottery winners. You might wonder why everyone in the room won the lottery. The answer is obvious. Only the winners are in that room. Similarly, only in universes where the constants allow for life would there be observers to ponder the question. The miracle of our universe's life-supporting properties is no miracle at all. It's a cosmic tautology, a self-selecting reality. The implications for your sense of uniqueness are profound. You are not a special creation in a singular universe. You are a statistically probable outcome in one of an infinite number of quantum-spawned bubbles. Your universe is not the entirety of existence. It is merely your local cosmic neighborhood in an unimaginably vast landscape of realities. And this landscape itself, the metaspace, where eternal inflation churns out new universes, is just the larger canvas upon which these quantum fluctuations play out. It removes the notion of a universe that was designed for you, replacing it with a universe that merely happened to have the right parameters for you to exist and observe. This grand cosmic vista of infinite, fluctuating universes simultaneously liberates and diminishes. It liberates in suggesting that anything is possible, that every conceivable reality might exist somewhere in some bubble. But it diminishes in implying that our own universe, with all its wonder and complexity, is just one among an endless, meaningless array of random experiments, a single, albeit spectacularly successful, roll of the quantum dice in an infinite casino of creation. And the knowledge that countless other universes are being born, living and dying entirely beyond your reach, entirely separate from your own reality, adds a layer of cosmic loneliness to your existence. You are forever confined to your own quantum bubble, a prisoner of a single, fortuitous fluctuation in an unending ocean of possibilities. The sheer improbability of our universe emerging from a random quantum fluctuation, yet possessing the exquisite fine-tuning required for life, is a concept that truly stretches the limits of human understanding. It's akin to winning a lottery, where the odds are not just trillions to one, but literally beyond astronomical, numbers that exceed the number of atoms in the observable universe. And yet, here you are, a sentient being capable of contemplating this very improbability. This is the heart of the cosmic lottery ticket scenario. Consider the fundamental constants that govern our universe. The strength of the strong nuclear force, which binds protons and neutrons together in atomic nuclei. The electromagnetic force, responsible for light, chemistry, and holding atoms together. The gravitational constant, which dictates the pull between masses. The masses of elementary particles like electrons and quarks. The cosmological constant, which drives the accelerated expansion of the universe. If any of these values were even slightly different, often by amounts as minuscule as 1 part in a million, or even 1 part in 10^120 in the case of the cosmological constant, the universe as we know it would not exist. For instance, if the strong nuclear force were just 2% stronger, protons would pair up too easily, preventing hydrogen from forming, and stars would burn out too fast. If it were 2% weaker, no heavy elements would form beyond hydrogen and helium, precluding the existence of planets or complex chemistry. If gravity were slightly stronger, the universe might have collapsed back on itself long ago, or stars would burn too quickly. If weaker, galaxies and stars might never have formed. The precise balance is truly astonishing. In a universe born from a single, random quantum fluctuation, with no underlying design or purpose, these values should, in theory, have arisen randomly. The chances of them aligning perfectly for life would be infinitesimally small, making our existence a statistical anomaly of unimaginable proportions. This is where the notion of the ianthropic principle gains its full power. As discussed, if there are infinite universes, each a unique quantum fluctuation with its own set of random constants, then it's not surprising that we find ourselves in one that is life-permitting. We couldn't possibly exist in any other. The universe that supports you is, by definition, the one you inhabit. But let's pause and consider the philosophical implications of such a cosmic lottery. It means that your existence, and the existence of every complex structure around you, is not a product of divine intervention, not the inevitable march of cosmic evolution, but a random, statistically improbable fluke. There is no grand plan, no ultimate destiny inherent in the universe's origin. It just happened to hit the jackpot. This perspective can be both liberating and terrifying. Liberating in that it frees humanity from the burden of a predetermined cosmic role. Terrifying in that it strips away any inherent meaning from our existence beyond what we ourselves create. The universe becomes a vast, indifferent casino, and you are merely one of the countless outcomes, the key winner of a game you didn't even know you were playing. And for every universe that hit the jackpot, there are infinite others that resulted in cosmic dead ends, universes that fizzled out in a nanosecond, universes of pure radiation, universes where only a single, stable particle could ever exist. Our universe is simply a successful experiment in a blind, unthinking process of cosmic genesis. It removes the comforting notion of exceptionalism and replaces it with the stark reality of statistical inevitability given enough trials. This also implies that the rules of our universe are not necessarily fundamental in a universal sense. They are merely the specific, random parameters that happened to materialize in our particular quantum fluctuation. Somewhere in the vast multiverse, there could be universes where the laws of physics are so different that concepts like causality, time, or even stable matter don't exist. Our reality is just one specific instantiation of quantum possibilities, one brief, improbable blip in a sea of infinite what-ifs. The challenge then becomes, how do we distinguish between a truly designed universe and a statistically favored one in a multiverse? From within our own bubble, with its finely tuned constants, the evidence would look the same. We could never look outside our fluctuation to see the myriad others that failed. We are eternally confined to our lottery-winning ticket, unable to verify the existence of the infinite losing tickets. This makes the hypothesis difficult, if not impossible, to directly test, forcing us to grapple with its philosophical ramifications more than its empirical proofs. So when you look up at the stars, you're not just seeing the grandeur of a singular cosmos. You might be gazing upon the accidental triumph of a quantum fluctuation, a universe that beat unimaginable odds to simply be. And your existence within it is a testament to that incredible, improbable, and utterly contingent victory. It's a universe that whispers not of purpose, but of chance, not of design, but of a cosmic lottery that, for reasons we may never fully comprehend, simply happened to land on the number that allowed you to ask these very questions. Your reality is a fleeting cosmic moment, an accidental masterpiece born from the relentless probabilistic churn of the quantum vacuum. If our universe sprang from a quantum fluctuation, then the nature of the quantum vacuum, the nothingness from which it originated, becomes arguably the most crucial and perplexing aspect of its existence. And here, physics presents us with one of its most profound and embarrassing mysteries, the vacuum catastrophe. This isn't just a minor discrepancy, it's a colossal, mind-boggling mismatch between theory and observation that hints at a fundamental misunderstanding of the very foundation of reality. According to quantum field theory, the vacuum is not truly empty. As we've established, it's a seething ocean of virtual particles constantly popping in and out of existence. Each of these fluctuations, each of these ephemeral energy packets, contributes to the overall energy density of the vacuum. When physicists attempt to sum up all these theoretical contributions from all the known quantum fields, gravitational, electromagnetic, strong, weak, Higgs, the calculated energy density of the vacuum turns out to be an astronomically large number. In fact, it's so large that it predicts a vacuum energy density that is roughly 10 or 120 times greater than what we actually observe. But let's not lose sight of the central, mind-bending point. The entire observable universe, with its billions of galaxies, its complex structures, its fundamental constants, and your very consciousness, might be nothing more than an immensely improbable but statistically inevitable puff of existence from an eternally bubbling quantum vacuum. It's a universe that effectively paid for itself with borrowed energy, an energy debt that totals to approximately zero when you sum up all the positive energy of matter and radiation and the negative energy of gravity. Our universe could be the ultimate free lunch, a transient, self-consistent bubble arising from the quantum foam, a cosmic manifestation of the universe's inherent unpredictability at its most fundamental level. This means you're not just living in a vast cosmos, you're living in a cosmic lottery ticket that somehow won, against odds so immense they make winning. The actual lottery seemed like a certainty, and all of it from its fiery birth to its inevitable end. plays out within the boundaries of a grand, yet utterly random, quantum event. If our universe truly is a quantum fluctuation, what does that imply for its fundamental stability, its permanence? The very term fluctuation suggests transience, a brief deviation from a baseline that eventually returns to its original state. This concept plunges us into the unsettling idea that our entire existence, every star, every galaxy, every planet, every moment of consciousness you have ever experienced could be inherently ephemeral, a fleeting puff of existence destined to eventually dissipate back into the nothingness from which it arose. It's a universe living on borrowed time, not just in the poetic sense, but in the most literal, physical interpretation of quantum mechanics. Think about the virtual particles we discussed earlier. They pop into existence and then almost immediately annihilate, ensuring that the total energy of the vacuum remains constant over any measurable period. This is the universe's strict accounting principle for energy conservation. But what if a fluctuation is so immense, so profound, that it manifests as an entire universe? Such a universe would still, fundamentally, be an energy debt that must eventually be repaid. The total energy of a closed universe is believed by some theorists to be exactly zero, with the positive energy of matter and radiation perfectly balanced by the negative gravitational potential energy. This zero-energy universe concept is what allows for a universe to emerge from nothing without violating the conservation of energy. It's the ultimate sleight of hand. The universe appears as if it has enormous energy, but in its totality, it has precisely none. However, a zero-energy universe born from a fluctuation raises profound questions about its longevity. If it's a temporary excursion from the vacuum state, then logic suggests it must eventually return. This isn't a slow, entropic decay or a violent big crunch. It's a fundamental retraction, a reabsorption into the primordial void. The universe, in this view, is like a massive, complex bubble that inflated dramatically but is ultimately unstable. Its existence a temporary perturbation in a grander, more fundamental meta-vacuum. Could it simply wink out of existence, collapsing back into an indistinguishable state of quantum foam? The idea is chilling. Your reality could be nothing more than a temporary aberration, a magnificent but ultimately transient statistical blip. How would such a collapse manifest? Would it be a reversal of the Big Bang, a big crunch accelerated by the very forces that created it? Or something far more subtle, a gradual dissipation, a fading from existence that occurs not with a bang, but with a whisper, as the fundamental constants that maintain our reality slowly drift back to a state that cannot support complex structures. This isn't just about the heat death of the universe, where everything becomes cold and dark and diffuse. That's a process within the universe. This is about the universe itself ceasing to be, its stage dissolving, its actors vanishing, and even the laws that govern it being reabsorbed into the featureless, pre-cosmic quantum vacuum. Consider the existential weight of this. Every ambition, every achievement, every memory, every future dream, all predicated on the assumption of a stable, enduring reality. But if our universe is a quantum fluctuation, then its very foundation is built on contingency, on a chance event that could theoretically be undone by another chance event. We are, in a profound sense, living in a moment of cosmic grace, a statistical anomaly that has persisted for billions of years, but with no guarantee of eternal continuation. This fragility adds a layer of poignant beauty and desperate urgency to our existence. The universe, in this light, is not an eternal stage, but a temporary exhibition, a breathtaking display that will eventually be packed away as if it never existed. The physics here is speculative, pushing the boundaries of what we can currently observe or measure. But the theoretical framework of quantum cosmology, where the universe itself is treated as a quantum object, strongly suggests such possibilities. The Wheeler-DeWitt equation, for example, is an attempt to describe the wave function of the entire universe, a single equation that encompasses all of reality. In some interpretations, this equation suggests a universe that tunnels into existence from nothingness, a process entirely governed by quantum probabilities. These are not deterministic births. They are statistical events, meaning that our universe is fundamentally not a certainty, but a probability that simply happened to resolve itself in our favor. And just as it tunneled into existence, might it not tunnel back out? The timescales involved would likely be incomprehensibly vast, perhaps far beyond the expected lifespan of stars or galaxies, or even the proton itself. So this isn't an immediate threat, but a deep, underlying truth about the potential contingency of everything. We're not just living in a universe that began. We're living in one that might not have begun, and one that might, in the unfathomable depths of cosmic time, cease to be in a way that goes beyond mere decay or dispersion. It might simply cease to have ever been, its existence a grand, beautiful, and ultimately ephemeral, statistically improbable dream of the quantum vacuum. You are, in essence, a fleeting thought in the mind of the cosmic void, a momentary ripple on an eternal, turbulent sea of nothingness. If our universe is a quantum fluctuation, a singular, improbable event, then it opens the door to an even more mind-boggling concept, the multiverse. You see, the very nature of quantum fluctuations is that they are ceaseless, random, and ubiquitous. If a single fluctuation by sheer chance can lead to an entire universe, then why should it be the only one? This logic naturally leads to the idea of an infinite ensemble of universes, constantly bubbling up from the quantum foam, each a unique, self-contained reality born from its own improbable quantum genesis. This concept ties directly into the theory of eternal inflation. In this model, the inflationary period, which we discussed as the rapid expansion phase of our own universe, doesn't just happen once and then cease everywhere. Instead, it continues indefinitely in some regions of a larger multiverse. Imagine a vast, ever-expanding metaspace where inflation is eternal. Within this inflating metaspace, pockets or bubbles of space occasionally drop out of the inflationary phase. These bubbles then stop inflating and begin to evolve according to their own internal physics, potentially becoming universes like our own. Our universe, in this grand scheme, is just one such bubble, one quantum fluctuation that managed to inflate and solidify. These bubble universes would be utterly distinct and causally disconnected from each other. They would be separated by vast, ever-expanding gulfs of inflating space, making inter-universe travel or communication fundamentally impossible, much like the way galaxies beyond our cosmic horizon become unreachable in our own expanding universe. Each bubble would be an island of reality, a self-contained cosmic experiment. And here's where the idea truly gets wild. There's no reason to assume that the physical laws or fundamental constants would be the same in every one of these bubble universes. Imagine the sheer diversity. One bubble universe might have a different speed of light, another might have a stronger or weaker gravitational force, a third might have electrons with a different charge, or even a different number of spatial dimensions. Most of these universes would be utterly inhospitable to life, collapsing instantly or expanding too rapidly for stars to form, or having chemistry that simply doesn't work. But among the infinite permutations, by the sheer force of statistics, there would inevitably be some universes where the conditions are just right for complexity to emerge, for stars to ignite, for planets to form, and for life, perhaps even intelligent life like yours, to evolve. Let that number sink in, one followed by 120 zeros. It's not just a little bit off. It's the largest discrepancy between theory and observation in all of science. If the vacuum truly had this much energy, the universe would have either collapsed instantly under its own immense gravity, or expanded so rapidly that not even atoms could form, our universe, quite simply, would not exist. And yet, here we are. This is the vacuum catastrophe. The theoretical fury of the vacuum energy, if fully unleashed, would tear our reality apart, but somehow it is suppressed to an almost impossibly small, yet non-zero value. The small, positive value we do observe for the vacuum energy is what we call dark energy, the mysterious force responsible for the accelerating expansion of our universe. Dark energy, it turns out, is the observed manifestation of the cosmological constant, a term Einstein reluctantly added to his equations of general relativity and later called his biggest blunder before its modern rediscovery. But the problem isn't that dark energy exists. It's that its observed value is absurdly small compared to what quantum theory predicts for the vacuum energy. It's like predicting an elephant in your living room and finding a dust bunny instead, and then having no idea why. So if our universe is a quantum fluctuation, how does this catastrophic mismatch fit into the picture? Does it mean our very birth from the vacuum was somehow tuned to dampen this colossal energy? Or does it imply that the entire concept of the quantum vacuum itself, as we currently understand it, is incomplete or fundamentally flawed? Some theories suggest that a massive cancellation of positive and negative vacuum energy contributions must have occurred, perhaps through a mechanism yet unknown, leaving behind only the tiny residue we observe as dark energy. But such a precise cancellation, akin to balancing a mountain of positive numbers with a mountain of negative numbers to get a sum of exactly 0.0001, seems almost as improbable as the initial quantum fluctuation itself. Perhaps the universe's emergence from a fluctuation is the explanation. If the universe started as a tiny bubble of quantum foam, perhaps it selected a vacuum state where this cancellation was already inherent, or where the borrowed energy was precisely balanced by the negative gravitational potential in a way that left only this tiny, observable dark energy residue. It's as if the universe, in its very act of fluctuating into existence, performed an exquisite act of cosmic self-regulation, suppressing the vacuum's true potential fury to allow itself to persist. This profound mystery, the vacuum catastrophe, makes the idea of a universe born from a quantum fluctuation even more challenging, and yet, in a strange way, more compelling. It suggests that the nothingness at the heart of reality is far more complex, far more powerful, and far more subtle than we can currently grasp. It's a nothing that has the potential to unleash an energy density so vast it would shred everything, yet somehow it gave birth to a universe where that energy is almost perfectly tamed. You are living in a universe that is, by all accounts, a magnificent improbability, not just in its birth, but in its very continued existence, held together by an almost perfect cosmic cancellation of forces. The vacuum's fury, theoretically immense, is somehow restrained, allowing for the gentle glow of galaxies instead of an immediate, catastrophic annihilation. This implies that the quantum fluctuation that spawned us wasn't just a random blip. It was a blip of incredibly specific, self-regulating properties, a testament to a deep, underlying physics of nothing that we are only beginning to glimpse. It's a universe that exists because the vacuum, in its chaotic potential, decided not to be as furious as our equations suggest it should be, a cosmic act of self-restraint at the most fundamental level. The concept of our universe as a quantum fluctuation faces a significant hurdle. How could such a chaotic, random origin lead to a universe that is so remarkably uniform and flat on large scales? This is where the theory of cosmic inflation doesn't just provide an explanation. It becomes an essential, urgent embrace, a necessary mechanism to smooth out the initial quantum chaos and render our universe habitable and comprehensible. Without inflation, a universe born from a raw quantum fluctuation would be a jumbled, lumpy, and fundamentally inhospitable mess. entirely unrecognizable as the cosmos we observe. Imagine the universe in its earliest moments, a tiny, hot, dense speck born from the quantum foam. In this nascent state, quantum fluctuations would be rampant, creating tiny variations in energy density everywhere. These variations are the seeds of structure, but without a smoothing mechanism, they would be far too large and irregular. The universe would be incredibly lumpy, with huge temperature differences and uneven distributions of matter. Such a universe would never form stars, galaxies, or the large-scale structures we see today. It would be a cosmic disaster, an immediate collapse, or an explosive dispersion, utterly devoid of any potential for complexity. This is where inflation steps in as the cosmic homogenizer. As we discussed, inflation is a period of ultra-rapid, exponential expansion that occurred immediately after the Big Bang, driven by a hypothetical field called the inflaton. During this brief, unimaginably fast expansion, where space itself stretched by factors of at least 10^26, two critical things would happen to the initial quantum fluctuation. First, any significant curvature of space-time within that initial fluctuation would be stretched out to an almost perfectly flat state. Think of a tiny, crumpled piece of paper that you then inflate to the size of a continent. Its surface would appear incredibly flat from any local perspective. This solves the flatness problem, explaining why our universe's geometry is so close to Euclidean, a necessary condition for its long-term stability and the formation of large structures. Second, and perhaps even more critically, for a quantum fluctuation-born universe, inflation would smooth out all the initial quantum irregularities and anisotropies. Any pre-existing lumpiness in the energy density would be stretched so thin, so uniformly, that the universe would become incredibly homogeneous on large scales. It's like mixing a tiny drop of ink into a vast ocean. The ink spreads out and effectively disappears into the uniformity of the water. But here's the subtle genius of inflation. While it smooths out the pre-existing quantum fluctuations, it also generates new ones on cosmological scales. During inflation, the quantum fluctuations of the inflaton field itself would be stretched and magnified, becoming macroscopic classical perturbations. These newly generated fluctuations, amplified by inflation, would then become the seeds for the large-scale structure of our universe. They are the tiny temperature differences observed in the cosmic microwave background, CMB, which later grew through gravitational attraction into the galaxy clusters, superclusters, and cosmic voids we see today. So ironically, the very mechanism that takes a chaotic quantum fluctuation and turns it into a coherent universe also imprints the residual signature of quantum fluctuations onto the cosmos. The patterns in the CMB, the baby picture of the universe, are not just random noise. They are the echoes of quantum fluctuations from an unimaginably early epoch, stretched across billions of light years. They are the direct evidence that something quantum, something probabilistic, happened at the universe's origin. Without inflation's urgent embrace, our universe, born from a quantum fluctuation, would have been a cosmic anomaly that never had the chance to evolve beyond its initial chaotic burst. Inflation acts as a filter and an amplifier. It filters out the destructive, large-scale quantum chaos, homogenizing the universe, while simultaneously amplifying the smaller, more subtle quantum jitters into the very scaffolding upon which galaxies would eventually form. It's the critical bridge between the weird, probabilistic world of quantum mechanics and the grand, ordered structure of the cosmos. Without this period of rapid expansion, the idea of a universe emerging from a simple quantum fluctuation would likely fall apart, unable to account for the uniform, flat, and structured reality we inhabit. The enduring mystery, of course, is what triggered inflation and what caused it to end. In the context of a universe from a quantum fluctuation, the inflaton field itself would be a product of that initial fluctuation, a specific energy configuration that allowed the universe to tunnel into its inflationary phase. It's an urgent, powerful, yet incredibly specific mechanism that lends credibility to the idea of a universe born from chance, but then rapidly shaped by physics to be habitable. You exist in a universe that was snatched from the jaws of quantum chaos by an unimaginably powerful, yet temporary cosmic force, a testament to the universe's ability to self-organize from the most improbable of beginnings. If our universe is a quantum fluctuation, then the nothingness it arose from isn't truly empty. This leads us to confront the profound concept of the quantum vacuum, a realm so enigmatic it makes black holes seem straightforward. This isn't just about virtual particles popping in and out of existence. It's about the very nature of empty space, which, far from being a void, is a dense, energetic medium, a dynamic backdrop against which all cosmic events unfold. And the biggest shadow cast by this nothingness is dark energy. Dark energy is the greatest mystery of modern cosmology, accounting for approximately 68% of the total energy density of the universe. We know it exists because its effects are undeniable. It's causing the universe's expansion to accelerate. Galaxies are not just moving apart, they're moving apart faster and faster. This isn't due to the kinetic energy of matter. It's due to a persistent, pervasive force acting on space itself. And the leading candidate for dark energy is, chillingly, the energy of the quantum vacuum. Imagine every cubic centimeter of empty space. According to quantum field theory, this space is filled with the zero-point energy of all quantum fields, the lowest possible energy state of these fields. Even at absolute zero temperature, these fields retain a certain irreducible amount of energy due to quantum fluctuations. This is the vacuum energy. If our universe is a quantum fluctuation, then this vacuum energy is not just a background phenomenon. It is the very fabric from which we emerged, and it continues to exert its influence on the cosmos. The problem, as discussed with the vacuum catastrophe, is that the theoretical value for this vacuum energy is ridiculously large, while the observed value for dark energy is tiny. But the very fact that we do observe a non-zero positive vacuum energy density, even if incredibly small, is a crucial piece of the puzzle. It means that the nothingness that surrounds us, and from which we might have sprung, is actively shaping the fate of the universe. It's not a passive void, it's an energetic entity, a constant underlying force that will ultimately determine the universe's long-term future. In the context of a universe from a quantum fluctuation, dark energy could be seen as the residual energy signature of that initial spontaneous creation. The universe borrowed a vast amount of energy to come into being, positive energy of matter, radiation, balanced by negative gravitational potential energy, but it appears to have kept a tiny, persistent amount of pure vacuum energy as its birthright. This residual energy is what we call dark energy, and it's slowly but inexorably pushing everything apart. The philosophical implications here are profound. If the universe's origin is a fluctuation, and its ultimate fate is dictated by this persistent vacuum energy, dark energy, then our entire cosmic story is bookended by nothing. It begins with a quantum blip from the vacuum and ends with an ultimate dispersal into a vast, empty expanse dominated by the very same vacuum energy. The universe, in this sense, is an elaborate, temporary manifestation arising from, and eventually returning to, a more fundamental, energetic nothingness. The accelerating expansion driven by dark energy means that in the distant future, all galaxies outside our local group will recede beyond the cosmic event horizon. They will become forever unreachable, their light so stretched and redshifted that they will vanish from view. Future astronomers in a Milk-Dromedar supergalaxy will see only darkness beyond their local cluster. The universe will appear as a single, isolated island of stars in an infinite, expanding void. This isolation, this ultimate cosmic loneliness, is orchestrated by the very energy that hints at our universe's quantum birth, dark energy. The shadow of nothingness is actively erasing evidence of the vastness and diversity of the cosmos for future generations. It's a force that is not only defining our present, but also reshaping our future, ensuring that the universe we inhabit becomes increasingly empty and desolate. This isn't just about astronomical distances, it's about the fundamental properties of space-time being stretched and diluted by a persistent background energy that arises from the quantum vacuum itself. You are living in a universe that is being slowly but surely unraveled by the very nothingness that birthed it. The quiet, persistent force of dark energy is a constant reminder that our magnificent cosmos is ultimately a battleground between gravity, which pulls things together, and the expansive power of the vacuum, which pushes everything apart. And in this battle, the vacuum energy seems to be winning, gradually ensuring that all complex structures will become isolated, and eventually the universe itself will revert to a state of cold, dark, and almost perfectly empty space, a final echo of its origin in the primordial quantum foam. The shadow of nothingness, far from being passive, is an active, inexorable force, constantly reminding us of our universe's fleeting, temporary grace. The idea of our universe arising from a quantum fluctuation intertwines deeply with one of the most unsettling aspects of quantum mechanics: the role of the observer. In the subatomic world, particles don't have definite properties until they are measured or observed. They exist in a state of superposition, a blur of possibilities, a wave function that only collapses into a definite reality upon interaction. If the entire universe in its nascent stage was a quantum fluctuation, does this mean our very existence as conscious observers somehow collapsed the universe into its current state? This is the profound and deeply philosophical observer's dilemma. Imagine the universe before it existed in a classical sense, a primordial quantum fluctuation. It would exist as a superposition of all possible universes, all possible constants, all possible histories. A universe where gravity is strong, one where it's weak, one where carbon forms, one where it doesn't. A quantum wave function of the universe encompassing every conceivable reality. According to some interpretations of quantum mechanics, this vast superposition only resolves into a single, definite reality, the universe we inhabit, when an observer comes into being. This isn't to say that a conscious being with eyes and a brain necessarily needs to exist for the universe to become real. The concept of an observer in quantum mechanics is much broader, often referring to any interaction or measurement that causes a quantum system to lose its superposition. But if the universe itself is the quantum system, and it persists in a superposition of states until some form of self-measurement or internal observation occurs, then the emergence of conscious life within that universe takes on an almost terrifying significance. Could it be that the universe existed as a blurred potentiality, an uncollapsed wave function, for billions of years, only truly solidifying into its observed classical state upon the arrival of conscious beings like us? This idea, while provocative, faces enormous conceptual challenges. It implies a form of cosmic solipsism, where reality is fundamentally dependent on sentience. Most physicists argue against such an anthropocentric view, suggesting that interactions within the early universe itself, the formation of particles, the first stars, the first galaxies, would have constituted sufficient observations to collapse the cosmic wave function into a definite reality long before the emergence of life. However, the observer's dilemma still casts a long shadow over the quantum fluctuation hypothesis. If our universe truly is a statistical blip, then its existence might be fundamentally linked to the probability of it being observed. The many worlds interpretation of quantum mechanics, for instance, posits that every quantum measurement causes the universe to split into multiple parallel realities. each corresponding to a different outcome of the measurement. If our universe originated from a quantum fluctuation, then perhaps it branched off into an infinite number of universes, each representing a different resolution of its initial quantum state. In this scenario, you, the observer, are simply in the branch where the fluctuation led to a life-permitting universe. You haven't collapsed the wave function. You've merely found yourself in one of its countless manifestations. The philosophical weight of this is immense. Your role, your consciousness, your very act of questioning the universe's origin might not be a passive reflection of an independent reality, but an active, if unwitting, participant in its ongoing definition. You are not just a product of the universe. In some profound sense, you might be an integral part of its self-realization, a cognitive echo of its initial quantum becoming. It shifts the entire paradigm of existence from a predetermined stage to a dynamic, observer-influenced canvas. This dilemma forces you to confront the limits of your own perception and the boundaries of scientific inquiry. Can we ever truly understand a universe whose very nature might be contingent on our ability to observe it? If the universe is a quantum fluctuation, then perhaps its deepest truths are forever veiled behind the veil of probability and the inherent ambiguity of quantum reality. You are in essence trapped within the outcome of a cosmic measurement, a living testament to a universe that decided to be, and in doing so allowed you to perceive its being. The universe, in this view, is a grand, unfolding quantum experiment, and you are both the experimenter and the result, a product of the very process you are attempting to comprehend. The line between observer and observed, between reality and perception, blurs to an unsettling degree, leaving you suspended in a cosmic enigma where your consciousness might be the final, crucial component in the universe's journey from potentiality to actuality. If our universe is a quantum fluctuation, emerging from nothing, then the chilling question naturally arises, must it eventually return to nothing? The very word fluctuation implies a temporary deviation, a transient event that ultimately reverts to its initial state. This leads us to confront the ultimate demise, a cosmic end that goes far beyond the familiar scenarios of heat death or a big crunch. This isn't merely the universe dying, it's the universe unexisting, its very fabric dissolving back into the primordial quantum vacuum from which it momentarily sprang. Consider the various fates physicists envision for our universe. The most widely accepted, given the accelerating expansion driven by dark energy, is the heat death, or big freeze. In this scenario, the universe continues to expand, cooling and diluting until all stars burn out. Black holes evaporate via Hawking radiation, and the universe becomes a cold, dark, empty expanse where energy is spread so thinly that no further work or organization is possible. This is a death of activity and structure, a slow, entropic fade. Another possibility, if dark energy increases in strength, is the Big Rip. In this extreme scenario, dark energy would eventually become so powerful that it would overcome gravity. Then the strong and weak nuclear forces, tearing apart galaxies, solar systems, planets, and even atoms themselves, literally ripping the fabric of space-time apart. This is a violent, ultimate destruction, a shredding of all reality. But if our universe is a quantum fluctuation, its ultimate demise might be even more profound and unsettling. It might not be a death in the traditional sense, but a detunneling or a reabsorption back into the meta-vacuum. If the universe tunneled into existence from nothing, borrowing energy to create its vastness, with positive matter energy balanced by negative gravitational energy, summing to zero, then the universe is fundamentally an unstable state, a temporary perturbation in the grand quantum foam. The laws of quantum mechanics that allowed it to pop into existence might also dictate its ultimate return. Imagine a quantum particle existing for a brief moment, then disappearing. Now scale that up to the entire cosmos. Our universe could be a gigantic, billions of years long quantum event that, at some unfathomably distant point, will simply tunnel out of existence. It wouldn't necessarily be a violent crunch or a slow fade. It could be a sudden, instantaneous erasure, a cosmic reset button pressed by the underlying quantum mechanics. The fabric of space-time itself would unravel, matter would cease to be distinct, and all the laws of physics that govern our reality would dissolve, leaving behind only the turbulent, probabilistic chaos of the primordial vacuum. This kind of demise is fundamentally different from a heat death or a big rip, because it suggests that the universe was never truly permanent. It was always a temporary construct, a cosmic illusion sustained by a delicate balance of quantum probabilities. The entire saga of cosmic evolution, from the Big Bang to the formation of life, would be just a brief, statistically improbable detour in the eternal dance of the quantum vacuum. And what would that look like for you if you were to somehow witness it? It wouldn't be like watching stars die or galaxies disperse. It would be like observing reality itself lose coherence, its fundamental building blocks ceasing to obey the rules, its very existence dissolving into an indistinguishable background noise. The timescales for such an event are purely speculative, likely extending far beyond the 10-100 years predicted for black hole evaporation or the even more distant future of heat death. But the theoretical possibility is profoundly chilling. It implies that our universe, for all its majesty and complexity, is merely a magnificent, fleeting blip in a larger, unchanging, and ultimately indifferent quantum reality. Our cosmic story, from beginning to end, is a chapter in a much longer, unwritten book of quantum probabilities, a book where chapters are constantly being written and erased in an endless cycle of creation and annihilation. You are, in essence, living in a temporary arrangement of quantum fields, a self-consistent illusion that has persisted for billions of years, but one that is ultimately destined to dissolve back into the ultimate nothing from which it arose. The universe isn't just fragile, it's a transient phenomenon, an exquisite, improbable dream of the quantum vacuum. And its ultimate demise might not be an end, but a return to the silent, seething, eternal potentiality of the void, a cosmic memory that once erased will leave no trace that it ever existed. Your very being, your thoughts, your experiences, all fleeting manifestations of a cosmos destined for ultimate unexistence, a grand, beautiful, and profoundly ephemeral quantum anomaly. The notion that our universe is merely a quantum fluctuation weaves a profound and often unsettling narrative about the very meaning of existence. If the cosmos burst into being from a random statistical blip, with no predetermined path or grand architect, then the traditional concepts of purpose, design, or an overarching cosmic plan are fundamentally dismantled. You are not a meticulously crafted outcome. You are a lucky roll of the cosmic dice, a fortunate consequence in a vast tapestry woven entirely by chance. Imagine a universe without inherent purpose. If it arose from a random fluctuation, then its intricate laws, its beautiful structures, its capacity to support life are not the result of intelligent design, but of a statistical lottery. The fine-tuning that allows for carbon-based life, the precise balance of forces, the consistent arrow of time, all of these are simply the specific parameters that happen to manifest in our particular fluctuation. Out of an infinite number of possible fluctuations, ours just happened to be the one that allowed you to ask these very questions. This is the ultimate demotion of humanity from a central special role to a statistically probable outcome. This perspective can be deeply unsettling for many. It challenges millennia of human thought, which often seeks meaning and purpose in a universe that seems to be ordered and comprehensible. If the universe's genesis was fundamentally arbitrary, then any meaning we ascribe to it, any purpose we find in our lives, must be entirely self-created. There is no external cosmic validation for our hopes, dreams, or struggles. They are significant only to us within the confines of our fleeting, accidental reality. The universe in this light isn't a story with a beginning, middle, and predetermined end. It's a dynamic, ever-changing pattern emerging from chaos, a complex, self-organizing system that just happened to coalesce in a way that allows for consciousness. The cosmic tapestry is not designed. It is simply unfolding moment by moment, guided by probabilistic rules rather than an overarching script. And your life, your consciousness, your entire civilization is but one thread in this immense, unplanned, and ultimately indifferent fabric of chance. This leads to a profound sense of existential liberation, coupled with an equally profound sense of cosmic loneliness. On one hand, you are free from any predetermined destiny or imposed cosmic burden. You are free to create your own meaning, to define your own purpose, without the weight of an external cosmic agenda. On the other hand, it means that the universe itself is fundamentally indifferent to your existence. It didn't want you to be here, it simply allowed you to happen. And in the vastness of an infinite multiverse of fluctuations, your unique bubble of reality, with all its joys and sorrows, might be just one of countless, ultimately insignificant permutations. The very concept of value becomes a human construct. The beauty of a nebula, the elegance of a mathematical equation, the profundity of a human connection, these are not reflections of an inherent universal order, but interpretations, emergent properties of a conscious mind within a statistically favored fluctuation. The universe is not inherently good or evil, purposeful or meaningless. It simply is a grand, undirected experiment in quantum probability. This is not to say that the universe is without wonder. On the contrary, the sheer improbability of it all, the fact that such a magnificent, complex reality could arise from pure chance, can inspire an even deeper sense of awe. The cosmic tapestry, woven by countless random quantum threads, creates patterns of unimaginable beauty and complexity. The accidental nature of our existence makes our struggles, our triumphs, and our capacity for love and creation all the more poignant and precious. Because there's no guarantee, no grand design. Every moment becomes a testament to the improbable miracle of being. So, when you reflect on your place in the cosmos, consider the profound shift in perspective that a quantum fluctuation origin implies. You are not a protagonist in a divine play. You are an emergent phenomenon in a universe that just happened to work. Your life, your consciousness, your entire reality is a fortunate accident, a brief, luminous flash of order in an eternal dance of quantum chaos. And in that realization there is a stark, profound beauty. The universe doesn't care if you find meaning, but it allowed you the capacity to create it for yourself. An ultimate act of self-determination in a cosmos born of chance. You are the ultimate self-made meaning, a fleeting, beautiful pattern in the cosmic tapestry of probability. If our universe truly emerged from a quantum fluctuation, how would we ever know? The profound philosophical implications are compelling, but science demands evidence. And it turns out the universe has left us a faint but incredibly powerful echo of its quantum birth, literally etched across the fabric of space-time. The cosmic microwave background, CM radiation. This ancient light, the earliest we can possibly detect, is a direct fossil record of the universe when it was just 380,000 years old, long before the first stars formed. And its subtle patterns are precisely what we'd expect from a universe born from quantum jitters. Imagine the universe in its infancy, incredibly hot and dense, a plasma of protons, electrons, and photons. Light couldn't travel freely. It was constantly scattering off free electrons, making the universe opaque. But As the universe expanded and cooled, electrons combined with protons to form neutral hydrogen atoms. Suddenly, the universe became transparent, and the photons were free to stream across space. This light, stretched by billions of years of cosmic expansion, is what we detect today as the CMB. It's a uniform glow of microwaves coming from every direction in the sky, a perfect blackbody spectrum at a temperature of about 2.7 Kelvin. But the CMB isn't perfectly uniform. Embedded within this ancient light are tiny temperature variations, hotter and colder spots differing by only about 1 part in 100,000. These aren't random splotches. They form a specific pattern, a power spectrum that can be precisely measured. And these tiny temperature fluctuations are incredibly significant. They are the gravitational seeds from which all the large-scale structure of the universe, galaxies, galaxy clusters, and vast cosmic voids eventually grew. Now, here's the crucial link to our quantum fluctuation hypothesis. According to the theory of cosmic inflation, which, as we discussed, is essential for a quantum fluctuation to grow into a coherent universe, these initial density fluctuations were not created by some classical process. They were generated by the quantum fluctuations of the inflaton field itself, magnified and stretched to cosmological scales during the period of rapid, exponential expansion. These quantum jitters, inherent to the vacuum, became the macroscopic irregularities we observe in the CMB. The remarkable thing is that the observed pattern of these CMB fluctuations, their statistical properties, precisely matches the predictions of inflationary cosmology, which is itself rooted in quantum field theory. The CMB shows a nearly scale-invariant spectrum, meaning fluctuations exist on all scales with slightly more power on larger scales, exactly as predicted by models where quantum fluctuations were stretched during inflation. This is not just a qualitative agreement. It's a quantitative, highly precise match between theory and observation. Missions like the WMAP and Planck satellites have mapped the CMB with extraordinary precision, and their data provide compelling evidence for inflation, and by extension, for the quantum origin of the universe's initial conditions. But the echoes might not stop there. Another, even more subtle prediction of inflationary models rooted in quantum fluctuations is the existence of primordial gravitational waves. These are ripples in space-time itself, generated by the violent expansion of inflation, analogous to the quantum fluctuations of the inflaton field. These gravitational waves would leave a specific, swirling pattern in the polarization of the CMB light, known as B-modes. Detecting these B-modes would be a smoking gun for inflation and a powerful confirmation of a quantum-driven birth of the cosmos. While initial claims of their detection were later retracted due to foreground contamination, the search for these primordial B-modes continues with next-generation experiments. So, when you look at the CMB, you are literally gazing at the ghost of a quantum fluctuation. You are seeing the universe's baby picture, but within that picture you can discern the faint, statistical patterns born from the underlying quantum foam. It's a universe that, in its very structure, carries the indelible fingerprint of its probabilistic, quantum origin. The CMB is not just a relic. It's a cosmic Rosetta Stone, translating the language of quantum uncertainty into the grand, sweeping narrative of cosmic structure formation. This means that the universe isn't just a quantum fluctuation in theory. It has left behind empirical evidence, a measurable signature that points directly to its origin in the weird, probabilistic world of quantum mechanics. You are living in a universe that is constantly whispering its quantum birth story through the ancient light that surrounds us. And in these faint whispers, we find not a grand design, but the beautiful, intricate, and utterly improbable consequences of a cosmic roll of the dice. A universe that, against all classical odds, simply decided to be, leaving its quantum calling card for us to discover billions of years later. If our universe is truly just a quantum fluctuation, then the very concept of time, which seems so fundamental to our experience, becomes a fragile emergent property, a fleeting mirage that arose alongside space and matter from the primordial vacuum. This challenges our intuitive understanding of time as an absolute, ever-flowing river, suggesting instead that it's a consequence of our universe's particular quantum beginning, rather than a pre-existing stage upon which the cosmic drama unfolds. In classical physics, time is an independent parameter, a universal clock ticking away uniformly for everyone. But in the quantum realm, and especially in the realm of quantum gravity, time behaves very differently. Some theories of quantum gravity, like loop quantum gravity or string theory, suggest that time itself might not be fundamental. Instead, it could be an emergent phenomenon, a statistical average that arises from the entanglement and correlations of quantum events within the universe. Consider the Wheeler-DeWitt equation, mentioned earlier, which attempts to describe the wave function of the entire universe. A striking feature of this equation is that it does not contain a time variable. This problem of time in quantum cosmology suggests that at the most fundamental level, the universe might be static, timeless. What we perceive as the flow of time, the progression from past to future, could be an illusion, a thermodynamic arrow that emerges from the increasing entropy of our particular quantum fluctuation. If the universe sprang from a quantum fluctuation, then the start of time would be inextricably linked to that event. Before the fluctuation, there was no space, no matter, and crucially, no time. Time, like everything else, would be born in that instant of cosmic genesis. It wouldn't be a pre-existing container for the universe. It would be part of the universe itself, an internal property that emerged as the quantum fluctuation inflated and cooled. This means that before the Big Bang isn't a moment in time. It's a conceptual realm where time, as we understand it, simply didn't exist. The arrow of time and the irreversible progression from past to future is intimately linked to the second law of thermodynamics, which states that entropy or disorder always increases in a closed system. Our universe started in a state of incredibly low entropy, the highly ordered, hot, dense initial state, and has been expanding and becoming more disordered ever since. This increase in entropy gives time its direction. But if the universe is a quantum fluctuation, then this initial low entropy state itself is a statistical anomaly, an improbable starting point that allowed the arrow of time to emerge and point relentlessly forward. Without that initial, low-entropy quantum fluctuation, there might be no discernible arrow, no perceived flow of time. In a timeless quantum vacuum, events don't happen in sequence. They exist as probabilities. The emergence of our universe from this vacuum and its subsequent inflationary expansion would create the conditions necessary for entropy to increase, thus giving birth to the perception of time itself. Your every memory, your every anticipation, your very experience of duration, all are rooted in the statistical anomaly of the universe's quantum genesis. This implies that time isn't an external fixed reality that governs the universe. It's an internal, relative phenomenon, a consequence of the universe's internal dynamics, its expansion, and its journey from an improbable quantum state to an increasingly disordered one. Your personal experience of time, from the fleeting seconds of a heartbeat to the vast eons of cosmic history, is a fleeting mirage, a beautiful and complex illusion created by the universe's journey away from its highly improbable quantum birth. The philosophical implications are staggering. If time is emergent, then causality itself might be more nuanced than we imagine. The idea that cause always precedes effect, the very bedrock of our logical understanding of the universe, might be a feature that only exists within the confines of our particular quantum fluctuation. In the timeless, probabilistic realm of the meta-vacuum, such distinctions might be meaningless. You are, in essence, a creature of time, existing within a universe where time is a statistical consequence, a cosmic clock that began ticking the moment your particular quantum fluctuation decided to become real. This makes our lives, our brief flicker of consciousness, all the more precious and poignant. We are beings tethered to an arrow of time that emerged from chance, moving inexorably forward from an improbable beginning to an inevitable, timeless end. Your entire journey from birth to death is played out on a temporal stage that itself is a statistical consequence of a quantum event, a grand illusion that gives meaning and sequence to an existence that, at its deepest level, might be eternally timeless. The universe, in this view, is a temporal masterpiece, a fleeting mirage of duration, born from the ultimate nothing and destined to return to a state beyond the grasp of time itself. If our universe is a quantum fluctuation, then what lies beyond its boundaries? What is the unknowable outside from which it emerged? This question plunges us into the realm of ultimate unknowns, where our current physics and philosophical frameworks struggle to even formulate a coherent answer. Is it an infinite void, a larger meta-universe, or simply a conceptual frontier beyond which our very definitions of space, time, and existence break down? The very idea of an outside implies space. But if our universe created space in its quantum fluctuation, then there was no pre-existing space for it to be in. Similarly, if time began with the fluctuation, then there was no before. This means the unknowable outside is not a physical place in the way we understand it. It's a realm beyond our current conceptual grasp, a fundamental nothingness that defies our attempts to categorize or observe it. Some cosmological models, like eternal inflation, suggest that our universe is one bubble in a vast, ever-inflating metaspace where other bubble universes are constantly forming. In this view, the outside would be that eternally inflating metaspace, a larger reality where the process of universe creation is ceaseless. But even this metaspace would itself need an origin, pushing the question back one layer. What is the eternal inflation field? What existed before it? The rabbit hole of what's outside seems infinite. Other theories suggest the outside is simply the quantum vacuum itself, the fundamental ground state of reality, a realm of pure potentiality and probability. In this view, our universe is a momentary manifestation of that potential, a transient ripple on an infinite turbulent sea of quantum foam. The outside isn't empty space. It's the quantum field itself, existing in a timeless, spaceless state of probabilistic flux. It's a realm where causality, distinct particles, and even the laws of physics as we know them might not apply. This unknowable outside is not just physically inaccessible, it is conceptually inaccessible. Our scientific tools, our mathematical language, our very cognitive frameworks are developed within our universe based on its laws and properties. Trying to describe what lies beyond those laws and properties is like trying to describe colors to someone who has only ever known black and white. It pushes us to the very limits of what can be reasoned or imagined. The implication for your existence is profound. You are fundamentally confined to your cosmic bubble, your quantum fluctuation. There is no escape to the outside, no way to peer beyond the membrane of your own reality. Every star you see, every galaxy you observe, every theory you formulate, all exist within the confines of this one, statistically improbable cosmic event. You are a prisoner of your own genesis, forever contained within the boundaries of the fluctuation that gave you being. This doesn't mean the outside doesn't exist. It just means it exists in a way that is utterly foreign to our understanding. It could be a realm where the dimensions are different, where the laws of physics are inverted, or where the very concept of existence takes on a form we cannot grasp. It's the ultimate dark matter, the ultimate dark energy, a reality that influences everything but remains fundamentally hidden, beyond all sensory perception or scientific probing. The beauty and terror of this unknowable outside lie in its implications for contingency. If our universe is a fluctuation, then it is not necessarily the only one, nor is it necessarily the most fundamental. It is a temporary, self-contained system that arose from a deeper, more mysterious ground state. This imbues our existence with a sense of preciousness, but also a stark reminder of our ultimate insignificance in the grand scheme of an unknown, possibly infinite underlying reality. So, when you ponder the vastness of the cosmos, remember that even that vastness is contained within the confines of a single, improbable event. And beyond that event lies a mystery so profound, so utterly alien, that it pushes the boundaries of human thought itself. The unknowable outside is not just a spatial boundary. It's a conceptual horizon, a reminder that our understanding of reality is fundamentally limited by the very nature of our universe's quantum birth. You are an inhabitant of a universe that is a magnificent island in an ocean of ultimate, eternal, and utterly incomprehensible nothingness. As we reach the culmination of this cosmic journey, let's confront the ultimate truth derived from the idea that our universe is merely a quantum fluctuation. It implies a grand imprisonment of probability. We are not just confined by the vast distances of space, the immutable laws of physics, or the relentless march of time. We are, at our very core, imprisoned by the statistical improbability of our own existence, a magnificent, complex accident that, against all odds, resolved itself into the reality we perceive. Imagine the universe as the outcome of a single cosmic dice roll. That dice has an infinite number of sides, each representing a different configuration of physical laws, fundamental constants, and initial conditions. Our universe, with its capacity for stars, galaxies, and intelligent life, is just one such side, one statistically improbable result that happened to yield a reality capable of producing observers like you. The grand imprisonment lies in the fact that we are, and always will be, constrained by the particular outcome of that solitary, accidental roll. This isn't a physical prison with walls of expanding space. As we explored in previous discussions about intergalactic travel, this is a prison of parameters, a cage constructed by the specific values of the fine-tuned constants that allow carbon chemistry, stable atoms, and the emergence of complexity. If the strong nuclear force, the electromagnetic constant, or the cosmological constant had been infinitesimally different in that initial quantum fluctuation, our universe would have been a cosmic wasteland, incapable of supporting life, or perhaps would have collapsed or ripped itself apart before any consciousness could arise. We are imprisoned within the very parameters that define our existence. The philosophical implications of this probabilistic imprisonment are profound. There is no inherent purpose, no preordained destiny, no guiding intelligence behind the creation of our cosmos. It is a product of pure chance, a statistical anomaly that by the sheer force of quantum probability simply happened. This can be a terrifying realization, as it strips away the comforting narratives of cosmic design and human exceptionalism. You are not the center of creation. You are an incredibly fortunate byproduct of a random quantum event, a sentient ripple on an indifferent sea of probability. Yet there is also a profound melancholic beauty in this imprisonment. The very fact that such immense complexity, such exquisite beauty, such profound consciousness could arise from pure chance, from a fleeting blip in the quantum foam, is an astonishing testament to the universe's inherent capacity for self-organization. Our prison then is not one of limitations imposed by a hostile universe, but one of boundaries set by the very conditions that make our existence possible. We are defined by our improbable origins, forever bound to the specific quantum outcome that allowed us to be. The grand imprisonment also extends to our understanding. If our universe is a quantum fluctuation, and other fluctuations give rise to other universes with different physical laws, then our ability to comprehend the ultimate nature of reality is fundamentally limited. We are confined to observing and understanding the laws that pertain to our specific accidental bubble. The vast, unknowable outside, the realm of other probabilities, remains forever beyond our intellectual grasp. A constant reminder that our reality is just one of an infinite number of possible cosmic outcomes. We are intellectually imprisoned within the confines of our own statistical reality. So, when you gaze at the night sky, you are not merely looking at billions of stars. You are contemplating the improbable triumph of a single quantum event. You are seeing the magnificent, intricate architecture of a universe that, against all odds, decided to be, and in doing so created the very conditions for your consciousness to perceive its being. Your existence and the existence of all you hold dear is a testament to an unimaginable cosmic lottery win, a fleeting, precious moment of order in an eternal dance of quantum chaos. This is your cosmic situation, a prisoner of probability, confined to a universe that is both a statistical miracle and an accidental masterpiece. You are living in the grand, improbable outcome of a quantum fluctuation, a universe whose existence is a fleeting, beautiful defiance of nothingness. And in understanding this profound imprisonment, you gain a unique perspective on the preciousness and contingency of all existence. Our universe might be a quantum fluctuation, but it is our quantum fluctuation, and within its improbable boundaries lies infinite wonder, awaiting exploration. Thank you for joining me on this journey to the heart of cosmic contingency. If this exploration of our universe's quantum origins has shaken your perception of reality, please share this video with someone who looks at the stars and wonders. Subscribe to continue exploring the mind-bending realities and profound implications of our cosmic situation. Remember, you might be a statistical anomaly, but you are a conscious one, capable of contemplating the very probabilities that brought you into being. What other cosmic mysteries should we unravel? What other grand imprisonments has the universe constructed? Leave your thoughts below, and let's continue to map the boundaries of our magnificent probabilistic cage together. Until next time, keep looking up at the stars, even knowing they are part of an accidental masterpiece. Sometimes understanding our imprisonment is the first step toward finding ultimate meaning within it. If you are still watching, make sure to subscribe to the channel and give a thumbs up. And if you want to keep exploring the mysteries of the universe, I'm sure you will love this other video at the left side of the screen. We just found out the universe is a hologram. In this video, we explore the mind-bending theory that our entire 3D reality might just be an illusion, a projection from a 2D surface at the edge of the cosmos. See you there. Thanks for watching.